Okay, I'm Raman Tiwari, going to present about how we are using Flink to build a real-time session store and power a lot of machine learning and recommendation at Netflix. With me, I have Brian and Julian, who will also be talking about similar systems and part of this system. And hopefully you'll learn something out of this talk. Goals. So goals are kind of very broad for this, but essentially we want to build a system that can serve real-time user interactions of what members or users are doing in Netflix app to our machine learning and recommendation systems with very low latency, so that we can respond to the things that users are doing in near real time. With that, we are going to talk about two systems which are built in kind of similar principles of using Flink in a really stateful manner to kind of keep this user state and act on it. First of those systems is Fluid. It stands for Profile Level User Interaction Data Store. So as you can see, like when you open Netflix, the very first thing we do is ask your profile, which profile you want to use to experience Netflix. And that is because all the personalization and recommendations are done at profile level. Sometimes same person will create multiple profiles and kind of train Netflix the way they want that profile to recommend, right? So you have kids profile, you have adult profile, which are different in different tastes. So what does that mean to us? It means to us that we do want to kind of look up all this data or index in technical terms by profile ID, so we can query those things in real time and kind of act on it. Now this system is built on a concept of session. Session for us is basically a period of activity followed by a period of inactivity. So if you interacted with Netflix for say 10 hours long and then you go to bed, then your session ends. As simple as that. There's no other fancy definition. Session is just a period of activity followed by inactivity. Now, what we are interested here with this system is capturing a lot of implicit and explicit signals. So what do I mean by explicit? Explicit is very simple. Like when you kind of like something, you're explicitly telling Netflix that, oh, I really like this title. Show me more like this. Or when you are clicking on certain rows or kind of doing horizontal scrolling or vertical scrolling, you're explicitly giving us those signals, right? Then there are a bunch of implicit signals, like how much time you are spending on different pieces of the page or row or section. How long did you play a trailer? You know, like you like some title, you played it, and then you quit after 2 minutes. Then those are implicit signals that we are also interested in capturing, right? So these are kind of a very simple list of things like focus or clicks, we call it, details page when you open a movie detail page, thumbs and stuff like that. So our goal with this system is to capture all these signals, process them and kind of find some meanings to it and then serve those meanings. So we are not interested in serving the raw events because raw events are like huge and there are so many ways you can interpret. We rather are interested in like some of the metric that we can serve to the user. So with that, let's do a live demo of what this system looks like, and then we will get into technical details.
One housekeeping question.
Yes.
Questions stuff loud, or what's the answer?
Yeah, we can make it more interactive. Ask whenever. No problem. Yes.
I'm a Netflix user and I have 2 kids, and I often found myself watching trailers, and then one of the kids needed to go to the toilet or I need to make popcorn. So how smart is the system to detect that it's kind of human change versus disinterest?
Okay, so in a nutshell, the question is like, if you're pausing a title, like how do we detect whether that was a human interaction versus some system thing? So we actually don't really care too much about that. We focus more around, you know, what is the level of engagement that you have, And if you have paused for a period of time which is logical enough for us to say that the user is inactive at that point, then we'll say, okay, this session is complete. Does that make sense?
Yeah, absolutely.
Okay. So I'm gonna try to do a live demo here. Hopefully I can. Live demos are always fun. Okay. So I have this kind of tool on the left-hand side that we call Fluid Viewer, where you can navigate or visualize these sessions, right? And then on the right-hand side, I'm going to, well, let me enable auto refresh on this one and also refresh the page. Okay. And then on the right-hand side, let me open netflix.com, select my tester profile. Okay, so far, we haven't done anything. There is some trailer playing on the right side. You see this red thing that appeared right now? It's like the live session, right? So user basically signed in, chose profile, and we have a session appearing here. Few key details. This is the profile of the user. This is when the session started. This is how long the session is, and this is how many events we have seen so far. Fluid has the concept of live session when the user is actively engaging, that we call a live session. Then there's a concept of historical session when the session is complete, followed by that inactivity. Let me increase this a little bit. So in this section, we are showing a bunch of metadata that about this user. We have a concept of navigation, which is the user journey through various pages of Netflix. So currently user is sitting in home page. User has kind of scrolled up or seen certain titles. So we are saying that the titles that were shown to the users were 13. User hasn't really done anything other than this autoplay that happened, right? Now I'm gonna do some actions here. For example, let's say I go to continue watching Bollywood drama, and I'm basically horizontally navigating into these, right? Like I'm navigating into these things. So we are able to, in real time, tell that these are the rows that user interacted with. And again, I'm going to talk about the architecture, but the first thing I want you to understand here is the low latency requirement of this system. We want this to work in millisecond latencies. That is how it is designed, right? So almost instantaneously, we are able to tell that user interacted with row number 5, is 0 index, so is row number 6. They have seen like 15 title on that particular row. They didn't engage with anything on that row, right? And this row was seen this many times. Similarly, I hovered over something, right? For example, I click on this, I go to movie details. So who killed Sarah appeared here almost immediately, right? It says that's the entity. User clicked on that title, then user opened the detail page for that particular scene. So we have the concept of like interactions, like what kind of interactions users are doing. And then there is a trailer being played, and we are able to capture that trailer right here. So it started at this time. A trailer has been playing for this much time. If I go to playback from here, if I play, there will be a playback entry here, right? So we are able to kind of capture that. Moving out, other interesting thing that happens on Netflix, like a large percentage of our playbacks are from search. So kind of addressing that use case was also very, very important. So we kind of designed search with in mind. So let me kind of search for, say, Brad Pitt movies. You see like another section appears here, says user searched for this. They are in the search page for this many seconds. You see, I'm kind of getting into dwell time a lot because this is a very, very important metric for machine learning. How long did they spend on what section of Netflix? So as a result of this search, user saw 20 titles. They didn't engage with anything so far. So let me go to this and maybe click on this one, click on, say, Top Gun. So here you see like there are two entries which we are able to correlate, right? So this is another very important topic in machine learning world called attributions, right? What happened as a result of what? what caused what, right? So if user search for Brad Pitt and then they clicked on certain things, we want to tell that those interactions were result of searching Brad Pitt. So we are able to kind of attribute these two things together. And finally, as user has navigated into different pages, we are able to tell that, okay, user opened the movie detail page, then they went to playback for this much time, then they went to home page again movie detail, and they are in search page right now. So we are able to also track users journey through different um, uh, parts of Netflix application, at the same time kind of tell you how long did they live at that particular time. Okay, so that's the demo. Now let's go back and understand, like, or talk about how it all works under the hood. Okay. Any questions so far? Very interesting. Cool.
Now I know you always monitor.
No PII was captured as a result of this. It's all, yeah, we are very mindful of that. I'm gonna skip this. This was if my live demo failed, then I was going to show you this YouTube video, but we can skip that. Oh, it did start playing. Okay, so use cases, I'm gonna quickly go through this. The primary reason we have this system is for machine learning and recommendation. And then there are a lot of secondary use cases, but primarily we want to capture those metric, the standard metric that are meaningful in the browsing history or browsing behavior of a user, dwell time, page views, journey, the whole journey I was showing around what sections of the page user has interacted with. We also want to do certain attributions. One of the very important attributions is like, how long did it take for a user to do a meaningful play? So for example, let's say we call a meaningful play for something that a video was played for, let's say 10 minutes, then it's a meaningful play. So it's very important for us to also know all the actions that user did to arrive at that meaningful play. If they struggled trying to find, they spent 20 minutes trying to find something to watch and then did a meaningful play, it's not a very good experience. If they were able to find something out of the rows that were recommended to them, it's a great experience. So we want to kind of understand that and do the attributions. Other example would be, did user like something or added to their my list before or after a meaningful play? So for example, if you played something for a decent number of minutes and then you did a thumbs up, that means that, oh, user did like the content, right? So something like that. Then we use this system for a lot of search personalization use cases, search ranking and stuff like that. And all of this depends on our ability to serve this in near real time. If this is stale, if this takes a day or two to deliver, then a lot of these use cases cannot be met. So the design of the system, and that's where Flink has been really, really useful for us.
Romel, go ahead.
Oh, so what I would want to understand is that from what you showed us as this application, this is where the Flink is doing the aggregation, but also pump the data into Druid. So what you actually see is the Druid on the top of it do another set of aggregation with the final result, or everything is coming out from Flink.
Great question. It's slightly more complicated. We'll get to the diagram to talk about all this, what piece is being doing what. But in a nutshell, if I heard Druid in this question, there's no Druid used here. All the aggregations are custom. We have our own aggregation library, which is running in Flink, as well as the service that is serving this data. And then we'll get to it. It will be slightly clear in a minute.
Okay.
Okay, let's do it then. That's better. Few goals that were in mind, other than the latency requirement that I guess I've talked about multiple times, we also want the data model of this user session to be really, really flexible. Meaning like you could add a new metric tomorrow. At the same time, we guarantee that you could never break an existing metric that were being served. And then the way we do it is by, like this session is basically a protobuf schema and where we never make like backward incompatible changes. So we are keeping this metric evolving without breaking any of the consumers. Lookup time median is less than 20 millisecond. For historical sessions is actually 4 to 5 millisecond, which is really, really quick. All these sessions or the data that you saw in the demo is also available in data warehouse for batch analysis. Let's say you want to do a large model training or over, let's say, year worth of data. So this data is sitting in a warehouse table for you to see that as well. Data attributions we have seen. Other key requirement of this system was to build it such that it's easily integrated with other parts of the algo and machine learning platform that we have here. We could have built this system in isolation and later figured out, oh, it's not really usable because it cannot integrate with the systems that needs this data. So there was another key design principle or requirement in this topic.
There's a question in chat. How many events per second does your system ingest?
7 million per second on an average. Yes. Okay, now we have Brian to talk about the architecture, and this is where a lot of the cool technical details will emerge. So Brian, take it away.
Hey everyone. So I'm going to be talking about how this stuff works that Remind just demoed. And I guess first I'll give kind of a really high overview of how our entire system works, and then I'll focus on this fluid system that we are specifically talking about. So if you start in the top left, that's where you have the Netflix client application. And so this is like the Netflix app that everybody is familiar with. And so this app is emitting events as you're using it. And these events are sent in batches, and it works by sending HTTP requests to the next component in the diagram, which is our ingestion service. Ingestion service is very simple. It's basically just receiving these HTTP requests that contain the events, and then it logs them to Kafka. And then that's when Flink comes in. So we have a couple Flink apps that I'm not going to go into a ton of detail, but they're basically doing enrichment and filtering on these events as they come in. And then we get into the fluid section of the diagram where we're reading these events, where we've already kind of selected the specific events that we care about for this use case. Fluid is processing those. It's kind of building up a list of events that form a session. And at the same time, it's writing these to a couple different data stores, which then make it possible for the final thing at the bottom of the fluid section, the fluid service that can query those data stores. And that's how our downstream consumers get access to the data. They send requests to the fluid service, and then the fluid service looks it up in those data stores. And I'm going to talk about this in a little bit more detail on the next slide. So this is kind of like the data flow diagram for. It's basically zooming into this blue box from the previous slide. So as the events come in, we are reading them off of Kafka. We do some basic transformation where we transform them into this protobuf format, which is how we interact with the data for the rest of its lifetime in Fluid. We key it by profile ID. Again, profile ID is that unique identifier, not just for a user, but for their profile within the account. And once the data is grouped in this way, we are appending it. We're into the Flink state. So the Flink state is basically storing a list of events for each profile ID. And then as this is happening, there's a batch timer that's firing every 1 second. So this is just using Flink's standard like timer mechanism. And this timer is basically taking those events and also appending them into a Redis cluster. So we use Dynamite, which is Netflix's layer on top of Redis that supports cross-region replication and a bunch of other features. But the basic idea is that the data that we're storing in Redis is pretty much a copy of the data that's stored in the Flink state. So it has all of the events. So as this is happening, there's another timer that eventually fires, once the session is complete. So let's say for a particular user, we haven't received any events in an hour or so. Then at that point, we will determine that their session is complete and it's time to basically clear out that live session data that's in Redis. So we send the delete request to Redis. At the same time, we take those events and we summarize them and we write them into a separate Cassandra store. So this allows our consumers to also consume data about the history of sessions for users. So we'll have the current ongoing session in Redis, and then we have the history of past sessions stored in Cassandra. We also output it to Kafka. That's how we eventually dump it into the data warehouse, as Romain mentioned earlier. So I'll talk a little bit more detail about how each of these components works. So first I'm going to talk about the Dynamite Redis part that's storing the live session data. Again, in the previous document that I showed, this is kind of the bottom right picture. So this is storing all of the live events. As the events are coming in, we kind of batch them up, and that we use some specific Redis data structures to make this possible. So we use the Z set. This is basically storing a set of unique events, or a set of unique elements. In our case, it's a list of events. That's handy for us because it allows us to dedupe if we ever get any duplicate events. We also use the H set, which is basically storing a map of data for a bunch of IDs. The reason that we do this is basically just a memory optimization. If you look at each one of our event objects, there's a component of it that's kind of repeated in a lot of them. This is sort of like the shared information, which might include like the user ID and a bunch of other stuff like that. So we kind of separate these headers out from the events and then write those separately into Redis. That allows us to kind of deduplicate a lot of that duplicated information and save memory in Redis. Yeah, so the nice features that Redis gives us for this is that it has really fast reads and writes, and it also allows us to, it supports these custom data structures like sets and maps that allow us to do incremental writes onto them. That's obviously faster than rewriting the entire list of events every second. And yeah, and the data gets replicated to all regions, so that's also helpful because we don't know exactly where the requests from our consumers might be coming. We don't want to have to guarantee that it will happen in the same region. So that was all about the live sessions. Now this is about the historical sessions. So I'm going to move this over so we can see the full. Oh, there are a few questions?
Yeah, so we
Sure.
wanted to answer them or choose to address them later. Right?
Probably later.
Okay, we'll do it later. Okay, yeah, we'll do the questions at the end. So yeah, so I'm going to talk about how we store the historical data. So when a session is complete, that's when we want to take it out of Redis and move it into Cassandra, basically. This allows us to store these sessions for much longer. When we initially developed this prototype of this system, we were also storing those in Redis. That allowed us to get pretty far and test it. But once we started wanting to store more and more of this data for longer, that was when we had to move it to Cassandra to basically for cost saving reasons. So we also make use of a specific system at Netflix that's called the Data Gateway Time Series service. This is basically a layer on top of Cassandra that makes it really efficient to store like time series event data in Cassandra. And that is exactly what we're storing here. Like if we think of each session as a record that has a timestamp, we want to be able to support range queries where we can say, give me all the sessions for this user that happened in the past 3 months or the past week, or whatever your time range may be. The time series service makes that really easy. It does some fancy things with basically partitioning tables into time buckets. So we have basically a separate table for each time bucket, and that allows us to avoid a lot of the slow compaction stuff that Cassandra normally has to do. It's possible to backfill this data. Yeah, so that's basically the details about how we store this data in Cassandra. Let's see, I'll go one more slide. And then this slide is just about a kind of project that we're working on right now to try and optimize the usage of Redis. So earlier I basically described the top row here, which is the V1 architecture of this. the V1 architecture, we are taking individual events, and basically the Flink job is forwarding those into Redis. Then when the users call our gRPC service to get a summary of that user's session, it will actually read all of those events out of Redis and then apply the transformation of those events into a summarized session record in place. This is very flexible, and it allowed us to iterate on the data model very quickly, because basically you always have a copy of all of your live data in Redis. You can query it, and if we want to tune this logic that transforms those events into a session, we can do that without having to backfill any data. The downside is that it's slower because we have to read all of this data out of Redis on each read request. Redis has to store a lot more data in memory, and we're starting to hit those points where like Redis would become unstable, or you'd have one of the Redis nodes go down and become unavailable. That was affecting the latencies and the availability of our service. So we wanted to try out something that's kind of a more reliable version of this, although we give up some of that flexibility. And the basic idea here is to do the summarization inside the Flink job instead of the service at the end. So earlier on in the pipeline, we're receiving these events in the Flink job, and then every second, instead of just taking that most recent batch of events and forwarding it into Redis, we actually rerun the summarization logic and produce the summarized session. And then we write that into Redis instead of writing the raw events into Redis. Then that basically makes it so the gRPC service at the end is a really basically a dumb like CRUD layer on top of the Redis data store. All that it does is just read that record out of Redis and then return it to the caller. So this is kind of a work in progress, but we think it's going to help a lot with our latencies and our reliability of this service. Yep. And now I'll go into Julian to talk about another system.
I will run through this very quick to get to the sort of more of the Flink pieces, but there we go. Okay, so similar to the last service, but with a couple of key differences. So Fluid maintains most user interactions, but importantly, part of that summarization process is that we do not retain all of the impressions that users had for those are summarized to just impressions that led to actual actions in Fluid. And so on the flip side of that, we need to have for a fair amount of time what users actually saw to power both machine learning and business rules. So we don't want to keep showing you billboards you don't interact with. We don't want to keep showing you the same fast laugh clips if you're trying to have just a short comedy hit. And we need to have this for 18 months. And so basically to break that down, we have two categories of questions. How many times has a particular profile seen a particular entity within the last N days? And then we have for our model training, given a profile and a particular time range, which entities did they see? And so that we can do this sort of negative inference that we showed you all of these impressions, you looked at them, you didn't watch any of them. Maybe we don't want to show those to you again, or wait until some other time. And then importantly, we also want to be able to know when you asked us this last Tuesday, what did we tell you? So that we can basically to both train models and to measure their robustness and sort of get a sense of what data we actually operated over at that time. We also sort of want to support this concept of time travel, which feeds into some of the design decisions. And so basically, we just want to know, given either for business rules, all like a full key and the event time it happened at, how many times. And for machine learning, we want to know with just a profile and a time range, and we want to get everything. And so basically one sort of important but easily forgotten thing with Flink is that you can build very, very complex stateful apps, and sometimes you do need to do that, like Fluid. You also can just break your app into small pieces and use Kafka streams and offline tables to maintain some of that state. particularly if it's useful to other systems. So those same client logs that power Fluid, we basically, a subset of those are kind of present, whatever gets presented on Netflix. And so we care about those. We care about those not just for this service, but across many of our personalization algorithms. And so we basically have split this logic into a number of Flink jobs. So we have sort of a source of truth app that kind of does enrichment and processing and flattening. And this would be, like we could imagine a app that produced all of these summaries, wrote them, held them in state and pushed them into another database to serve. But instead, we pushed these to basically just another Kafka stream. And we can ingest these both into an offline table. And so this we have another Flink job that basically handles, it reads from a stream, it at least once will deliver messages to the Kafka stream. And if you have to replay, okay, you get some replay there. And then we will also exactly once with a slight delay, push these to an offline table that we can query offline, we can run backfills from, et cetera. But that we can separate out sort of our state concerns of our processing and our actual writing with this intermediate step and still have very low latency real-time streaming because we immediately push to a Kafka stream and also have exactly once offline tables. And then from that, one of those consumers is another Flink job where we can basically extract just the few fields we care about for the impressions. Who did it? Where did they do it? When did they do it? And here, we can apply sort of our more complicated Flink operations. We can say, okay, we know that we have multiple delivery upstream of us. And so here we can use Flink state to deduplicate these impressions and, emit the first one, hold back subsequent ones, et cetera. And we can use, as we're pushing to our final database, we have sort of our network calls and we can reach, we want to have minimal latency, but we can deduplicate and have idempotent keys in our database. And so we can push everything through. And similarly to how we handled sort of at least once delivery for near real time and exactly once for more historical data, we can similarly, everything gets pushed through to the database. If we encounter errors, we can retry some number of times. If, database is down or we have a wrong key, et cetera, we can hold that in state until our next checkpoint when we flush again. If we still can't do it, we can push to a, sort of a dead letter queue and do offline processing there. But basically breaking all of the sort of complicated state management into separate pieces. And, the first piece of this job is a stateless job. The subsequent pieces do have state, but we don't need to maintain state sort of too far across checkpoint boundaries. Or if we do, we just need to maintain, sort of 16 bytes worth of information about them, or 16 bits, 2 longs, no bytes. And so, one sort of piece there was splitting it into lots of different pieces. And then similarly, with the gRPC architecture of that Fluid was talking about, these are possible failing network calls, but we can continue to retry them and eventually push them offline for future processing. And we get similarly low, digit millisecond latency end to end for best case and coverage of our, 18 months worth of impression data, so that if you watched Stranger Things season 3, we make sure that we show you the billboard for Stranger Things season 4 a year later, which is longer than most of our, we don't want to train everything over 5 years worth of data. Yeah, so your last slide.
Okay, hello again. I think next one, word challenges, I'll probably spend a minute on it and then get to question. We have like 24 of these already. So I think the biggest challenge here is logging inconsistencies, meaning the way individual features are instrumented across platform. For example, the way click is reported on TV is somewhat inconsistent from the way click is reported on web, right? So again, this system doesn't care about what device you watched in. We want to consistently say that user clicked on this for this amount of time. So kind of digesting all these inconsistencies and working around them was a big challenge. It's still a challenge. We try to identify and fix as much as we can, but there's always a tail end of devices where these things just never get rolled out. Tail latencies from offender. This happens generally when the whole ingestion system you saw in the diagram is a batched system, and sometimes a batch is sitting in your device and then you turn off your TV. So that batch at the end will be delivered the next time you turn on your TV. So you'll have these tail enders where the event happened maybe 7 days before when it's actually arrived in the server. So how we handle that? Scaling we already covered. Yeah, so late arriving data, and then at Netflix, unfortunately, we have so many, like maybe hundreds of IDs which are tracking different things. So kind of working around those IDs, finding the right meaning of individual IDs sometimes is really challenging because those IDs might have been created like a decade back and still being carried forward. So what is the scope of that ID? When does it get logged, and how long is that valid is another super challenging part for us. And lastly, in terms of Flink, I think state management has been really difficult after a point, because again, like all this is replicated everywhere. So the point is we tried really hard at the beginning to kind of optimize the event structure by doing that normalization where you have a header of all the metadata which is common to the user that never gets repeated. And then all the state in Flink is already binary. So we are storing protobuf, we are not storing raw events. So everything is binary. Even after that, state can reach to lots of like hundreds of terabytes. And then making sure that when you are rolling back and rolling forward, in this case, like it's very important to not miss that state in rollback. Otherwise, your session is gone at that point. That's like the source of truth right there. So kind of protecting that is another challenge. With that, let's go to questions. Any questions in the room? Sorry, folks on chat, I'll get to you. Yes, Shimran. Oh, why not Avro? So actually Avro is the incoming messages that you see here in the diagram. Sorry, real quick here. Up till this point, it's all Avro. But then we convert it to Proto right here. It's a great point, right? I've seen this question in chat also. The thing is like all these folks, right, in this layer, they work on Proto. This service, which is serving the event, is also a gRPC service, which is naturally Proto, right? So either we like kind of make our gRPC system work really well with Avro and try to do that. Avro also comes with like the requirement of doing some sort of a registry where you can sync the schema. So tomorrow, if I have like thousands of clients, like syncing that or providing that registry was another consideration. With Proto is really neat, right? Like your schema is packed with the client. It's not like there's no third service that you have to talk to. So again, bunch of reasons, but main reason is all the services which are the consumer of this gRPC service are just gRPC services. So Proto works naturally really well with that. Cool. Any other? Yes.
I had a question about Proto, but yeah, thanks.
Sure.
My question is about multi-region. How are you guys working and doing this optimization across multiple regions?
Oh, great point.
Yeah, if you are receiving, I imagine you're receiving events from multiple regions, but somehow.
Yes. So the question is, Netflix is a multi-region system, and it's possible that this client you see, like this web UI, might send events to multiple regions for the same session. So if we are running Flink applications separately in each region, you'll have this split brain scenario where, you know, part of the events are sessionized in one Flink app and then other part of the events are sessionized at the other Flink app. How do you reconcile that? So the reconcile is actually very, very hard because you have like state and your time ranges are kind of interrelated, then it's very, very hard. So the way we solve it is in the ingestion layer itself. So, so the ingestion service that we have has a feature that we call cross-region routing. So when a user session has started, we pin that wherever they landed, right? So which region handled the very first request is the home region for that user session. So we will guarantee that no matter what region you are arriving, your event will land to the home region before it gets processed to the next layer. So that cross-region routing is already handled here. And this we did not for just this use case, but this is a problem. And almost every week we do region failover exercises here. So last time I checked, about 11% of the time you are in a failover state where your events are split in multiple regions. So had to handle that before, but that's where it's handled. Next question. Any? Yes.
You mentioned about the profile level applications. You also have like a global application module like a course which shows the most popular. So
Oh. Yeah. So Julian's team does some of that, like let's say top shows that are popular right now. So some sort of popularity service, they are also extending that. One thing that we piloted as part of Fluid is kind of showing that Fluid can also do trends analysis on its own, right? In real-time trends. So one proof of concept application we built is we call trending searches. So if you're searching in Netflix, what are the top search items at any point in time, sliced and diced by country, language, blah, blah, blah. We build that. It's already like a kind of running dashboard. And then the way that we did is from this Flink app, we introduced a third output, and that third output was a Druid system where we ingest all the search terms in real time to Druid and then build a dashboard on top of that Druid data set. So let's say if we launch Squid Games, almost instantaneously we can see if the Squid Game search term is trending or not. So that's another feature of the system. Yes.
I just want to understand like the thing that we have, let's say I have the setup open at home versus a right? So do you have like different sessions, or are you saying like your device or like of the
right?
Yeah. All kinds of challenges and logics there.
Great question. So the question is the scope of session limited to profile, or if the same profile is active in multiple devices at the same time, are those same or different session? So the answer is they are different sessions. And when we sessionize, we are not only kind of grouping by profile ID, we also add device ID into it. So same profile being active on multiple devices will create multiple concurrent sessions, and they'll be summarized separately.
So let's take some questions on how that works. Oh, okay, one last one. Sorry.
Yes. Julian, you want to take?
Yeah.
Repeat the question.
Yeah, so the question is for exactly once semantics for offline data sets. How are we guaranteeing that? So one of the pieces is that because we push to Kafka Stream with at least once, we know that our online consumers will get data, and so we can use the with slight modifications, but basically like Flink has two-phase syncs to offline tables. And the downside of those usually is that you cannot read from them until you have a checkpoint duration has elapsed, so that you can confirm, okay, everything that we thought we wrote, we've now checkpointed and written. And so because we have we push to a Kafka stream at least once, everyone who needs online sort of near real time can consume from that. We just basically wait, and exactly once delivery offline is, we don't commit that we have consumed our checkpoints, our offsets to Kafka until we have confirmed that we've written a batch to our offline table. And the latency is less important there because we have a simultaneous online stream.
Correct. I'm gonna take maybe few from chat. Okay. Okay, so I think the Proto one. Oh, how do we determine the amount of time to wait? Sorry, I'm starting here, but let me know if there are. I think Proto and Avro we talked about. So it's already pre-decided. It's like a fixed amount of 30 minutes of inactivity where we cut the sessions. How to handle duplicate events out of order. So the ingestion layer already does some dedupe here. So if you send the same batch over and over, we will throw it away. We won't accept the second duplicate. And then that works by keeping a hash of the event that we are getting and then checking it against that using a really fast cache. So we do get, but that doesn't mean that we can't have duplicate. But if we do have duplicate, the sessionizer library that is running here and here takes care of two things, like ordering the events in the right order, and also deduping that. And that is possible because every event has something we call like a sequence numbers, and which is a monotonically increasing number starting with 1. The very first event will have 1, and then it will keep increasing. So if you get an event, if you get a bunch of events with the same sequence number, they are dupes. So we are able to throw them away. Is key by profile ID being done to make it more batchable? No, it is keyed on that because the session is actually created at profile and device ID. That's why we are using that. Curious, the trade-off Redis versus Flink state store. Great question. This one was a very big decision. Earlier we thought like, okay, if we have state or raw events in Redis, why even keep that in Flink? That's the very basic question people will be asking. And I think the logical choice there is in terms of checkpointing, right? Because if we ever have to go back and replay some data and you are not keeping your state married with checkpointing, then you are in trouble. You'll be out of sync. So you have to do additional work if your state is kept outside Flink to make sure that checkpoints are somehow tied to the state, right? So that's why it's kind of there. Are we at time? Okay, sorry, I can probably respond some of these offline. But again, thanks so much for joining, and over to the next presenter. So stop share.
Thank you very much.
Yeah.
All right, thank you. Awesome. So we have engineers from Pinterest who will present next. So take it away.
Thank you. Let me share my screen. You can see my screen, right? Okay. Hi, everyone. Welcome to our talk. Hen and I are software engineer at Pinterest. Pinterest is a social media, web and mobile application company. Our mission is to bring everyone the inspiration to create a life they love. Here's today's agenda. I will first go through introduction of our team and some history of streaming processing platform at Pinterest. Then I will cover some framework and services we have built to help onboarding new use cases to the platform. Then I will talk more about tools, use cases, and some of our ongoing projects. Feel free to ask questions during the presentation, and we will have Q&A at the end. Who we are? Our team is called Xenon. It's a streaming processing platform built on top of Apache Flink. It hosts low latency data processing use cases for long-running jobs. Right now, we are supporting 100 engineers built and nearly over 100 Flink applications. We run near real-time Galaxy API. We also run application on top of both raw Flink API and the Flink SQL. The platform currently is running with 10 million messages per second, and we process petabytes data every month. This team was built just 2.5 years ago. From the right side, we listed our tech stack. It contains 3 areas. First one is deployment stack, which includes CI/CD, job management service, Hermes, which is Pinterest deployment framework. We will talk about more later. The second area is developer APIs, includes near real-time Galaxy API, common library connector, and the Flink SQL. The last area is resource management and the job execution layer. Currently, we use cluster management on Yarn, but we are evaluating Kubernetes. It also includes job state management, which contains checkpoints, backups, and the security authentication, like how we control PI access using fine-grained access control. It also contains a tool called Dr. Squirrel, which we built to run job health and diagnose. Our platform has 3 missions. First one is stability. We're trying to reliably host all deployed Flink-based streaming processing application. The second mission is dev velocity. We would like to quickly productionize new use cases to meet our business and the product needs. The third mission is cost efficiency. We're trying to efficiently operate infra and strive to best practices. Some of our ongoing projects related to this, and we'll talk about more. Next, I will briefly talk about the platform history. Previously, we required a lot of manual work during the whole onboarding process. On the right side, you can see if user are trying to productionize their use case to our platform, it requires several steps. First step is user needs to create a pre-development form and make sure their job can run stable on dev cluster for at least 12 hours. Then they create a Jira ticket and assign to a Xenon, our team POC. We will review it. Second step is a user need to run load tests, use Xenon unifying source to simulate large traffic. They can also rate limiting to test those throughput. And they need to work on a staging verification doc to list all the things and the items they found during staging testing. If any issue found, they have to rerun the staging job again and do this test. The next step is if everything looks good after staging, user has to request a queue, a young queue, before they promote their job to production. Our team will create a queue and make sure enough resources are allocated before they launch job to production. If they want AZ failure resilient support, we will also make sure enough capacity was allocated on backup cluster in different AZ. So these steps involves like a dedicated Xenon POC work very closely with the customer during the whole process. It requires a lot of manual steps, and the median onboarding time was 37 days. So it was very, very painful. Made us realize we need to automate this process to improve dev velocity and reduce Xenon engineers' support load. Next, I will talk about some framework and services we built to help that. Like I mentioned, our first mission is stability. In this area, we developed deployment framework and the management service. Also, Verica helped a lot of some customer support ticket. So Xenon deployment framework, it's built on top of Bazel, Hermes, which is Pinterest deployment framework, and the backend job submission service with young clusters. Users first need to create a Bazel build file. Whenever they land a change to their repository, Jenkins job will look at the build file to see if it needs to build the Flink jar. A Jenkins job will also upload this Flink jar to S3 buckets and upload the Hermes deployment YAML file to Artifactory. Once Hermes YAML file contains all this deployment related information, on the UI side, it will constantly monitor Artifactory. Whenever it sees a new version of YAML file, it will display all the information on deployment page. User will be able to launch their Flink jobs using this YAML file. After user successfully launch a job, Hermes will convert this YAML file into a JSON format and pass to our backend job submission service. Job submission service read this YAML file and launch the job to young clusters. Right now, we have around 96 workloads running on Hermes. Workload is a deployment unit. Each CNON job can have multiple workloads for different environments like dev, staging, production. And we are supporting around 81 production use cases. Every day, on average, user creates 108 deployments through Hermes. Here are some work we have made recently. We've been focused on 3 areas. First one is stability. In order to onboard tier 1 application, we enhance the backend job submission service state machine and enable job level dedicated S3 buckets to reduce checkpoint latency. Tier 1 application has been running stably after those changes. Second area we worked on is improve user experience. We worked enterprise team in Pinterest to provide new features on Hermes UI, which include users are able to deploy jobs from most recent checkpoint. They can kill both jobs and distributed shell from the UI. We also enriched the SafePoint information like SafePoint trigger ID on Hermes. A user can also track daily and monthly deployment success rate. Another area we worked on is metrics. We exposed the job submission latency to StatSpot. After users successfully launched their job to production, we had 3 challenges. First one is, how can we monitor all production jobs' health? Second challenge was, once we detect production job fail, how can we fast recover them? The third one was to support AZ failure resilience, which is a critical requirement from tier 1 use case. If primary AZ or primary cluster goes down, how can we fast recover all production jobs to a backup AZ? That's why we designed and implemented job management service. It has 3 core features to address those challenges. First one is monitoring. Job management service monitor all production jobs by constantly checking job status, critical metrics like event processing QPS. It also checks checkpoint health, job manage and task manage health. If it detects failure, it will send out alert, notify users. The second core feature is auto recovery. If it found job failed unexpected, job management service will auto recover job in existing cluster from different states, including most recent checkpoint or certain save point or fresh state based on different requirements. The third core feature is AZ failure resilience. If the primary AZ or primary cluster goes down, this service will automatically fail over all the production job to backup AZ. This is a high-level architecture of job management service. We are familiar with the right side, which is user talk to Hermes and Hermes submit job to job submission service and launch application to Yarn. The left side, which we added to job management service, it will constantly monitor job status by querying Flink API and querying StatSpot and alerts to check critical metrics to make sure job not only running, but also processing data correctly. If cluster or AZ goes down, job management service will query Zookeeper to check Flink job status instead of relying on job submission service state backend machine. If it detects job failed unexpected, it will automatically recover or fail over job from correct state. Now this service is managing more than 60 production jobs, including tier 1, tier 2, and tier 3 applications. It provides fast recovery and reduce operation time by 90% from manual recovery to auto recovery. Customers no longer get paged in the middle of night, and they don't have to manually find the correct state and relaunch those failed jobs. On average, this service auto recovers failed job more than 7 times every week. Next, Heng will introduce more tools and our key use cases. Thank you.
Let me share my screen. Thanks, Rini. Okay. Yeah, I think one of the efforts I think Rini forgot to mention is the Veraka support. So actually, Veraka, we work with them. We work with Expert for over 9 months.
Can you go into presentation mode? Sorry.
I'm in presentation mode, right? No? Oh, you mean the, okay.
Yeah.
I see. I see. So,
thank you.
Full screen.
I think it's the top option. Slideshow.
Okay. Sorry. Oh,
There you go. Top option.
Oh, yeah. Yeah, I see. Okay. Yeah, I think another important area we want to mention is the support we get from the Flink experts. We work with them over 9 months, and we have over 45 issues resolved, and we have a few actively tracking issues. I think it provides a lot of support and values to help the stability of our platforms. Next, I'd like to talk about the second mission of our platform, developer velocity. So we have built a platform, but the most important part is we have get a Flink application running on our platform to meet business and product needs. So we have invest in 4 areas to improve the developer velocity. We have a CI/CD framework, we have a job debugging tools, we have a job development framework to allow writing Flink application much easier compared to using the raw Flink API. And also we have a working model. Basically, it is a streamlined process to convert an idea to a production Flink use case. Let's look at each one. So the first is the CI/CD framework. So what we want to build is we just want to bring the CI/CD practice from online services to the stateful streaming world. So there are so many CI/CD pipelines at Pinterest, but they are built for the online services. We leverage the same CI/CD infrastructure. We build a CI/CD pipeline, but it is highly customized for validating and deploying Flink-based stream application. The goal we want to achieve is straightforward, which we want to safely roll out user change or platform change with minimum human efforts involved in validation. As really mentioned earlier, there are a lot of manually validation done in the past, but with CI/CD, we can automate a lot of the validations, and we just wanted the users or the job developers to focus on the core business logic, and if they can write a unit test, it works, then very likely it goes to the CI/CD, it will work. If it doesn't, then we quickly get feedbacks, and they can get feedbacks through email or Slack notifications to fix the job. So let's look at the CI/CD pipeline details. Each pipeline basically consists of multiple components. So the first part is the trigger. The trigger is basically used to automatically trigger the pipelines based on the cron rule and the availability of new artifacts. And then it is a series of steps to check to do stability checks. As you may know, like we are like using the Spinnaker infrastructure to run the CI/CD pipelines, and Spinnaker is open source by Netflix. Thank you, Netflix. This is a great tool, and we leverage it and build the CI/CD pipelines and bring us a lot of values. So the checks we specifically do when we launch a CI/CD pipeline is a few parts, like a few like the job submission, As Renee mentioned earlier, our job submission involves multiple components. From the user click a job deployment on the UI to eventually get it running on the Yarn cluster, there are multiple systems involved. So when we do the CI/CD checks, we launch the job using the new artifact and make sure the job can eventually launch it successfully. After the job launches successfully, we check if there's restart loop. And also we check if a save point can be generated successfully. So basically, if a save point can be generated successfully, this means the job is actually making progress. And after we do these checks, we check matrix. So we use internally called the ACA matrix validation framework. Basically, we can, for each pipeline, add a list of matrix we want to validate. This can be any matrix, can be system level matrix, can be Flink job matrix, can be user-defined matrix. With this matrix and the threshold we specified, we can decide if the job is working okay or not, is generating the expected results or not. After the matrix validation, we do a little bit of chaos testing. What we do is we queue a job manager and see if the job can recover. And we randomly pick a task manager and queue that task manager and see the job can auto recover or not. So if all these checks passed, and we have very high confidence that the job will run okay in production. So the third part of the pipeline is production deployment. We have it is decider controlled, and it will basically deploy the jobs, deploy the new artifact to the production job during business hours if all the previous checks pass. We also have a user interface for the CI/CD. So on the right, you can see this is Spinnaker UI. It shows the detail of each pipeline execution. You can see the execution status. You can see the details of each stage. You can also see the pipeline parameters. On the left, this is the Hermes UI. Hermes is deployment framework really mentioned, but also part of the deployment framework, but it is also providing the UI for the CI/CD pipelines. So the Hermes UI, on the Hermes UI, we can see the pipeline execution history. It also allows simple operation like enable, disable the CI/CD pipeline, or manually trigger a pipeline execution. By default, it is automatically triggered based on the clone rule. And also it provides the links to the pipeline and provides the links to the Spinnaker. Very simple UI, very straightforward. Next, let's look at the job debugging tools. It is called Dr. School. So debugging a Flink job is never easy. So it requires relative deep knowledge about Flink. And it is also, when we debug a job issue, you need to kind of check many things. You need to check the Flink UI, you need to check the stats, you need to check the logs. There's so many information there. And from all this information combined, you want to find the root cause. It is never an easy task. And especially most of our job developers, like internal engineers, they probably never work on any streaming technology, or they never working on Flink. So it's really hard for them. And eventually this will come back to us, and we have to do it. But this is definitely not a scalable solution, as we are onboarding more and more use cases. So that's why Dr. School is built. Dr. School becomes the one-stop shop for Flink job troubleshooting. So the Dr. School basically surfaces suspicious stats to users instead of users searching for those things. Kind of check the GC, CPU, memory, back pressure, exception, bad configs, and many more. So it also provides instructions if it detects some suspicious stats. If it is simple, then I think the user can just take that instruction and redeploy the job with the instruction. If it is difficult, then come back to us. Basically, this Dr. School, these tools cut down the troubleshooting time and lower the required Flink internal knowledge to debug job issues and greatly improve the dev velocities. And here is a Dr. Score UI. You can see there are many information on this single page. There are health checks. Most of them are matrix. So and also we have exceptions. Those are the log links to those exceptions from the applications. And we also have configurations and as well as the URL links to like the yarn job link and the yarn UI, Flink job UI, as well as the dashboard, our matrix dashboard. The architecture of Dr. Score is consists of two parts. So the first part is the key part is the Flink job watcher. So this Flink job watcher itself is a Flink job. It consumes two Kafka topics. One is matrix, the other is logs. The matrix and log are generated and published from the Flink applications to the Kafka topics. And the Flink job watcher read this matrix, read these logs, and build a job snapshot and write the job snapshot to the Kafka topic. The second part of the Dr. Score is the web service. The web service consists of a Kafka consumer. It reads from the job snapshot generated by the Flink job watcher, and also it pulls many other informations from like dashboard, matrix dashboard API, from ACA, from Flink job manager, from the yarn resource managers, combine all the information we have and provide the latest job snapshot. The job snapshot is what you see, is basically the data that we see earlier on the UI. And the user can just go to the UI and see everything about these applications. And we make it simple. If it is all green, the job is okay. If there are some box that is red, if, for example, CPU or memory issues, then they can quickly take some actions based on the instructions. The third area we invest to improve the dev velocity is job development framework. So for the job development framework, we have several. We have the common library, the connector commonly used the source and the sinks. We have another currently light framework build. What I'm trying to talk about today is the NRTG. It's the short for near real-time galaxy. So it is a streaming version of the batch galaxy. The galaxy basically is a dependency injected framework, provide a data flow API, allow team to write and test the MapReduce jobs. So the near real-time galaxy has uses the same data flow API, but it extended to the streaming applications. So you can see the NRTG components involving multiple parts. But we are basically building everything on top of the data stream API. It works in this way. So users define a job. They use annotations to annotate the source and the transform. Under the hood, the Flink, the NRTG compiler will scan those annotations and convert those annotations, as well as the code people write into a Flink application using the data stream API. And there are many smaller and component involved, and also we make it easy to do config parsing, to do integration tasks, and also we support various data types. The majority use case at Pinterest are Thrift, but it can also support other commonly used serialization frameworks. So this is the NRTG components. So with this NRTG framework, it's like greatly simplified the job development effort, and the user can simply write I think NRTG signal probably in a few days or basically in a week, and we have all the support, and we can quickly bring it to production. So next, I'd like to talk about the fourth area we invest. We basically, it is a working model. It is called a production certification program. It is a streamlined process, consists of 12 tasks that require collaboration between the platform team and the job developer, so that we can quickly we can quickly convert an idea to production use case. What we provide as a platform is the so-called managed bootstrap of new use case. We can provide the best practices in terms of choosing framework and deciding the job graph. We also help with the dependency setup. In our at Pinterest, all these Flink use cases use many different internal services. So we have to set up those dependencies. For example, request some like a key value store segment. We need to adjust the rate limit to certain services. Those are all dependency setup. And also we provide a so-called a buildable and deployable skeleton project. So we are providing the Bazel build rules to build the job. We provide the Bazel build files to build the job. We have the skeleton Java code, skeleton test code, and as well as configs. And also we create the Hermes workloads, CI/CD pipelines, Yarn queues, as well as dashboard alerts with some default settings. So when we hand over this to the job developers, they can simply focus on testing and write and testing their core business logic. So the outcome of this process is we significantly reduced the onboarding time by 3 weeks. The third area of our platform is the cost efficiency. This is also the ongoing effort we are making. So basically, we are looking to do auto scaling of a Flink application. We want to automatically scale up and down based on the resource usage. Also, we are looking at doing that job health dashboard and the report. Earlier, we don't have much use cases, but now we have so many use cases. We want to calculate how much money like each job will cost, so that it can help to make the decision, whether we want to build the job, how we want to support the job. And the third areas where we are working on, as Vinny mentioned, is we're evaluating AWS EKS, and also we're looking to like solve the problems. Like we have so many Xenon cluster, but the load is not balanced. We're trying to figure out if we can balance the load across multiple Flink clusters. These are the areas we're working on. And also we're looking for collaborations and inputs, feedbacks from the community and the peer companies. If you want to do something together, you can feel free to reach out to us. We're more than happy to chat at these areas with you. Last, let's look at the use cases on Xenon platforms. So we are a new platform. So our platform GA'd in Q1 2020, and since then the number of use cases has grow a lot. By end of last year, we have over 80 applications. By end of Q1, we have almost 100 applications. We have this use case is basically starting and actually are transforming the data processing style of Pinterest from the batch style to the real-time or near real-time style. Let's look at a few use cases. We have so many use cases. I just picked 3. The first one is called ping stats analytics use case. This is one of the first use case onboarded to our platform. So it actually solved one of the user pain points. Our users, when upload a ping to the platforms, they really have like they really want something to track the stats of the ping in some like real-time fashion. So we used to have like a batch workflow to do this, but now we have this near real-time streaming job to calculate the ping stats. Another use case is the creator content use case. So when creator upload pings or videos to our platform, so we are building a lot of Flink applications, basically the ARTG applications to do this content understanding. We try to extract the signals from this content, and this help many downstream applications like trust safety, search, and recommendation. The last but not least, we also have a lot of infrastructure related use cases. So the team building the other team, like sister teams, building the real-time A/B testing based on the Flink application, based on the Flink, and to show the A/B testing results in near real-time fashion. Also, there's a user uptime as well as stats aggregation use case. The stats aggregation use case, I think, is used to build by the Spark streaming, as we Flink is the default platform and the long-term support platform at Pinterest. So they also build this Flink version of their matrix aggregation job. Yeah, I think, yeah, our team, this is all the team members. We are like engineers, PM, SREs, EMs, and we are hiring, and we're looking for collaborations to address some like common problems in the community. Now we're ready to take questions.
So I'm going to start with unmuting the microphone here in the room, because in that case, we'll give the priority for the people in person for people first. So anyone, if you have any questions inside the room, please feel free to come up here and speak in front of the microphone. Any questions for the Pinterest engineers in the room? Okay. So let's give the people here a few more minutes to think about it, and then why don't we move to the chat? And I think Rainy has already answered a few, but let's just kind of repeat those questions, because the audience here may not see those. So Rainy or Hang, can you please take a look at the chat box, the Q&A sessions? There was one question from there.
Sure. Rini, do you want to cover some of the questions you answered in the chat, and what are the?
Oh, sure. You would like? I think I answered some of them. Do you mean I can repeat the answers again here?
Oh, yeah. Maybe
okay.
Briefly mention that.
I see. So first question is Dr. Squirrel looks awesome. Thank you. Any plan to open source it? Yes, I think we will consider open source it in the future, but not right now. But thanks for the interest. Second question is how Flink state being managed in a Xenon platform. So we store checkpointing and save point data in S3 buckets, and we also use RockDB as local storage.
Yes.
The third one is someone from LinkedIn said we can chat more about stateful function if you are interested. Yes. Another one is, do we use Kafka? Yes, we use Kafka as input source. We also use Kafka as output sink to store the data. Curious, any of the Pinterest tool open sourced? Not yet, but we'll definitely think about open source some of the tools. Thanks for the interest. When do you want to answer the next one?
Oh yeah, I think, could you elaborate on any challenges while managing the Flink state? Yeah, I think I would like to talk about the different part related to the Flink state. We have raw Flink applications like the ping stats use case I just mentioned. I think the state is very large. I think the state can go to hundreds of gigabytes. So to make sure we can support hundreds gigabytes of state, we have a lot of basically we have a lot of task managers created to support that. And when we have a lot of task managers, the checkpointing and it becomes really hard. So because the checkpointing the task manager needs to communicate with the job manager during checkpointing, and we have so many task managers. Sometimes we see like checkpoint failures, and for that we basically tune the checkpoint related parameters so that we can safely, like we can successfully check create a checkpoint for those big jobs. I think another area I'd like to say about the Flink state is in our current version of the ARTG framework, the job development framework, we're not leveraging the Flink state. So basically we're leveraging the external services to do this state lookup. And And what we do is we add this state support in our ARTG framework so that we can do state check in locally instead of going to like external services to do lookup. I think the problem mentioned in the earlier talk is about the deduplications. I think the important use case of the state is to do deduplication. We use map state. We support map state in RTG so that we can do the deduplication easier. Instead of looking up a database, we can do that locally. And also it scales very well. Yeah, if you have more questions, we can always chat offline. The next questions, did you scale your infra dynamically? No, that's I think this is definitely on our roadmap. First thing we are looking at is how we can scale the Flink application, how we can scale up and scale down based on the traffic, based on the resource utilization. I think the next area, once we can, for example, scale up and down the jobs, then we can definitely look at how we can scale up and down the infrastructure. Are you planning to use the autopilot from Rorca or build? For that is ongoing effort. We are building something, leveraging the component we have built so far to build this auto scaling features.
Okay, so I think that's very good information. I really appreciate all the participants online joining us virtually, and also really appreciate the speakers, Rainy and Han from Pinterest. Thank you very much for putting all this together. Now, I think we are about to end the sessions online. For the people in the room, we may have a small surprise for you. So anything else from people online? If not, we're going to close the call. Okay, I think that's all good. Thank you very much.
you.
Have a wonderful afternoon and evening. Take care.
You too. Bye.
Thank you.